Chapter 11 is going to look at how one molecule or ion or atom will react with another ion, molecule, or atom, and how that has an effect on a lot of the properties such as viscosity, boiling points, melting points, and things like that. Okay, so let's start with a couple of definitions. So first one, we have been looking so far at what are called intramolecular forces. That's forces inside of a compound. So that positive, negative attraction in an ionic compound, and then that strength of sharing electrons in a covalent bond. So we're going to be talking about energies associated with a lot of these interactions. So for reference, a covalent bond is on the order of 100 to 900 kilojoules per mole, and an ionic bond, those lattice energies we talked about, on the order of 600 to 15,000 kilojoules per mole. So these are very, very strong. So what we're going to talk about with these other forces aren't going to be nearly as big as that. Some of them will be quite large, but intramolecular forces are going to be a little bit stronger. Okay, so intermolecular forces is the focus of this chapter. So an intermolecular force is a force of attraction felt between two or more molecules. Okay, so we're going to look at one molecule and how it might interact with another one. Okay, so all of these interactions are going to have to do with the polarity. So keep in mind when we do this, we are going to have, sorry, I want to go back. I just want a regular pen. Like I said, it's going to have to do with polarity. So remember, we have things that are polar and we have things that are non-polar. Okay, so that is going to be one of the largest factors that we are going to see when we look at these forces below here. So polar and non-polar, again, it's going to have a very large effect on this. Okay, so our first force is called a dispersion force. So it doesn't matter anything that you have, polar, non-polar, ion, doesn't matter. Everything experiences what are called dispersion forces. So that's an instantaneous dipole in a neutral molecule. Okay, so I'm going to explain kind of how that works, and then we'll go and look at some of sort of the properties and energies. Okay, so what happens is, let's, for example, say we have helium atoms. So this helium atom here has all of the electrons evenly distributed and is overall very neutral. This helium atom, for example, helium has 2 electrons. Let's say the electrons are over here on this side of the atom. Okay, so somehow in the randomness of the electrons moving in the atom, it turns out that both of the electrons are on this side. So that makes this end a little bit negative and this end a little bit positive. Okay, so this isn't permanent. It just so happens, statistically speaking, that sometimes your electrons can be on one side of the atom, and that's what we have here. So as this gets close to this helium atom that's nonpolar, that has, its electrons evenly spaced, it's going to push these electrons around in here or move these electrons. So let's say we have, an electron on each side of the atom. Because this side has that slight positive, that's going to draw these electrons over here because of that positive charge. And what we get is then a dipole produced in this otherwise neutral one. So since these electrons are moving over on this side, we're going to end up with this here, where we have that partial negative that was created by this atom here when those electrons moved because they were slightly attracted to that positive charge here. So instantaneous dipole. So what happens if we move these atoms away? So this happens because they're close together. This negative charge is felt, those electrons move because of that positive charge felt there. So if we move these atoms away, most likely what will happen is they'll go back to regular neutral helium atoms. When the distance is large, the electrons will go back to doing their random things and most likely being on other sides of the molecule or atom and not attracting whatsoever. Okay, so molecules can be polar or nonpolar to experience this. Again, it just so happens to be like the electrons happen to be on one side or not. Again, this is temporary, like we saw here. When we move those apart, the heliums went back to normal. It depends on the distance separating the two atoms or molecules. So when they were close, this was a lot stronger. And when we moved them farther apart, it weakened until the electrons essentially went back. Depends on the polarizability. So polarizability is the ease of distortion. So let's kind of think about things that would be easily distorted. Okay, so the first one is number of electrons. So for example, helium just has the 2 electrons. We're sort of counting on to produce this initial atom that we had to have both of those electrons on the same side of the molecule of the atom. Doesn't seem super likely to happen. It does, but let's say we had something like xenon that has so many more electrons. The probability that we can get a unequal distribution of electrons in something like xenon is far greater. So polarizability increases as the number of electrons increases. So one of the largest factors on polarizability is number of electrons. So we'll kind of make a note of that. I don't know, in purple here. So polarizability, the first thing is number of electrons. So again, more electrons equals easier to polarize. And number 2, we'll see this in a minute, the shape. So some shapes, some molecular shapes are easier to polarize. Okay, so that's what we'll look at kind of next. Okay, so, and we have that here. So first one, number of electrons. Next we have, again, that shape, and we'll talk about that. Okay, so what sort of energy are we talking about here? So dispersion forces are held together. So again, this would be sort of that force of attraction here, that dispersion force. That sort of magnetic force there that would hold those two together ranges from about 0.1 to 30 kilojoules per mole. So again, for reference, a lot of our covalent and ionic bonds, for covalent, hundreds of kilojoules per mole, ionic bond, hundreds up into thousands and 10,000s of kilojoules per mole. Okay, so we're talking about something far weaker than what we saw. Okay, so on the lower end would be something like helium, something that's nonpolar with not very many electrons. Over here on the upper end of this, you would have something that's probably lots more electrons and more easy to polarize, so maybe a better shape. Okay, so the next one is called a dipole force. So this is an electrostatic attraction between molecules that do have a permanent dipole. So this is 2 polar molecules. So we'll do a little highlighting there. So 2 or more polar molecules that are interacting. Okay, so since they already have that positive and that negative charge, it's a lot easier for those to interact. Okay, so let's kind of take a look. So we have HCl and another HCl. So because chlorine is much more electronegative, we have that pole of electrons this way and this way. Okay, so what that does is it gives us that positive charge for hydrogen, gives us the negative charge for chlorine, positive, negative. So what happens is that when these 2 molecules come together, the negative and the positive are attracted to one another. Okay, so negative and positive are attracted, and they form sort of a weak bond. Again, based off of, we do know that positive and negatives attract one another, so we do form that weak bond there. Okay, so drawing out the molecule here. So again, up at the top, these ones here, those covalent bonds. Again, we look up, we called those intramolecular forces. Okay, so what I circled there in green, those are the intra. And then we do have this here, and that was the intermolecular force. Okay, so two different molecules interacting with one another. Okay, so it depends on the distance separating the molecules. So if you get them closer together, that attraction is going to be much stronger. It depends on the polarity, so the strength of the dipole moment. So if you have a much larger positive charge on, say, like your hydrogen here, and a much larger negative, so if the magnitude of that dipole is more, then it's going to have a stronger attraction. So typically we say we see between 2 and 15 kilojoules per mole for a dipole-dipole force. Okay, so the next one you've probably heard of before. Scroll up here. And that is hydrogen bonding. So hydrogen bonding works the exact same way that dipole-dipole forces. The only difference here is you have a much larger magnitude, delta plus and delta minus. So you have a hydrogen on one in the atom attached to something very electronegative like oxygen, fluorine, and nitrogen. So those are our most electronegative atoms. So when you get a hydrogen bond, hydrogen attached to one of those, hydrogen being one of our sort of lesser of the in terms of electromagnetism, you get a very sort of larger positive and negative charge. So again, you have something like an HO. This delta positive and this delta negative are much, much larger than what we saw with a dipole-dipole. Okay, so again, it works the same way. So water is a good example of something that undergoes hydrogen bonding. So the oxygen is negative, the hydrogen is positive, and that attraction felt between that oxygen and that hydrogen creates that intermolecular force on the order of about 10 to 40 kilojoules per mole. So you're probably, I know a lot of you have taken biology, probably have heard this term before. It's DNA, water, lots of things, biological systems have some sort of hydrogen bonding mechanism sort of in their function. So this is a very, very important one. But again, we're not breaking any oxygen hydrogen bonds in the water. It's just one water molecule being attracted to another because this one is positively charged, this one is positively charged and this one is negatively charged. So we do feel that force of attraction there. Okay, the last one, our sort of largest magnitude of the forces here is called an ion dipole force. So kind of just like the name suggests, you have an ionic compound that dissolves into water, so you get cations and anions, or it doesn't have to be water, whatever your solute happens to be, and you get an electrostatic attraction between the ions in your ionic compound and the solvent, which is polar. Okay, so we get ions and a polar molecule. So that's where this comes from. So the easiest example is looking at salt dissolving into water. So we do know that salt does dissolve into water. So what happens is that water, being our very, very polar solvent, is attracted to both the chloride ions and the sodium ions, but in different ways. So let's take a look. So we see our chloride ion here. Here, I'll even make it the chloride color. We see the chloride ion here in the center with the negative charge. So it is going to be strongly attracted to all the hydrogens. So we see all of the hydrogens of the water pointing towards the chloride. So you're getting the Cl and, for example, the HOH of the water. That is our attraction here, our intermolecular force. That negative chlorine is attracted to those positive hydrogens. For the cation, which is what, purple? So for our cation here, it's not attracted to the hydrogens. It doesn't have the hydrogens pointing toward it. It has the oxygens. So now we have all of the oxygen atoms pointed toward the cation here. So we have the Na, and then for the water, we have the oxygens pointing towards it. Oops, got it, almost got it. There we go. So you have the oxygens pointing towards the sodium, and again, that sodium attracted to that oxygen is the ion dipole force. So again, these ones are our strongest ones. These ones are over 50 kilojoules per mole because again, you have a full positive and negative charge with your ion. And then a lot of times with things like water or these polar solvents, you get a strong attraction between the oxygen or the hydrogen in water. Okay, so that's our 4 different types of forces. So let's kind of review what we have and kind of make some kind of notes as we kind of go through. Okay, so dispersion forces. That can happen between anything. Okay, so dispersion forces between anything. So I'm going to sort of erase all of this so we can kind of make some notes. So again, dispersion forces happen between any types of molecules, sort of anywhere. Okay, so to recap, for a dispersion force, it can happen between a polar and a polar. It can happen between nonpolar and nonpolar, and it can happen between polar and nonpolar. Okay, so any combination of these types of things can produce dispersion forces. And again, if we look, a dispersion force is just kind of pushing electrons around. If you yourself have some sort of dipole, whether it be a permanent dipole, like we would see with polar, or whether it's sort of a spontaneous dipole, like we see with nonpolars. Okay, so this will happen with all of our different types of molecules. Okay, so this one, if we kind of look at this one here, this one was called dipole-dipole. Dipole is sort of short for polar. So this is polar with another polar. Okay, so it can be the same like we saw here with HCl, or it could be different. So we could have it with like HCl and SO2. So let's say we had HCl and we had SO2. Okay, so we would expect this to have dipole-dipole forces also between these two molecules, even though they're not the same. Okay, so we'd have the H and the Cl. Here we'd have the S and the O and the other O. And we would expect that to be our dipole-dipole force because our chlorine is negative and our sulfur would be positive because oxygens are more electronegative. So we can even see it between things that are different, like an HCl and an SO2. But so again, fall in this range here, but again, the key here was these were both polar. So our oxygens are the delta minus and this hydrogen is the delta plus. So again, anytime you have dipoles here, you can get a dipole-dipole interaction. Okay, so back to this page. So here again we had, essentially the same thing, but this time we had oxygen, fluorine, and nitrogen involved. So that's the key here. You have to have O, F, and N, okay, with each other. But everything about it is exactly the same. How it works, because you have the two things that are both polar, all of that is the same. It's just a stronger interaction because you are dealing with very, very electronegative elements of oxygen, fluorine, and nitrogen. Okay, but again, works the same. So this one, again, if we wanted to kind of do our recap, also polar molecule with another polar. And again, you have to have O, F, N attached to a hydrogen. And here you're looking for O, F, N attached to a hydrogen to get hydrogen bonding. Okay, so last one. Hopefully this one is a little bit kind of obvious what we have here. So for this type of interaction, your two types of molecules you have to have ionic with a polar. Okay, so you have an ionic solute and you have a polar solvent to get this type of interaction. So if you can figure out kind of what your molecules or your two things that are interacting with one another, you can narrow it down to which of these interactions it should be. Okay, so again, if you have something that's nonpolar, like CH4, you definitely can't have hydrogen bonding because it's nonpolar. And you definitely can't have dipole-dipole because it's nonpolar. It's not an ionic compound, so you rule this out. So the only thing that CH4 could have with another CH4 would be dispersion forces. So again, if you can identify if you have polar and nonpolar, it's going to help you put them into these different categories here. Again, they can be the same. We saw a lot of the same. So we're going to see a lot of molecules being the same because we are going to talk about properties. Like, why is the boiling point of this so much larger than something else? So again, we would be looking at two molecules of the same interacting with one another. Okay, but again, we did see on that previous example, they can be different. Okay, so what types of properties are we going to have or are going to be affected by these intermolecular forces? First is melting point and boiling point. Okay, so in order for something to melt, go from a solid to a liquid, or to boil, going from a liquid to gas, something important that has to happen is your forces must be overcome. Okay, so for example, if I had water, so HO, H. Okay, so if I wanted to, again, I'm going to do this yellow. That's my intermolecular force right there. So if I wanted to boil water, so I wanted this water to be able to escape into the gas phase, I'm going to have to break this interaction. Okay, so I'm going to have to physically separate these two water molecules. So we're going to have to physically separate those two water molecules in order to get the molecules to separate out into the gas phase. So forces must be overcome for molecules to separate and enter the gas or liquid phase. So what we're going to see when we look at melting and boiling point is the stronger the interaction, the higher, we'll just say boiling point, but that goes with melting as well. So we're going to see, for example, things that have hydrogen bonding are going to have much higher boiling points because those interactions are very strong. Things that have only dispersion forces are going to have very low boiling points because those interactions are the weakest ones. Okay, so we'll also see things like, for example, if you compare helium to xenon, we're going to see that have a factor as well, like the ease of polarizability. And then finally, we'll get into things like shapes. The way that different molecules are arranged is going to have an effect on their melting and boiling points also. All comes back down to the type of interaction and the polarizability. Okay, will affect our melting and boiling points, with the type of interaction being the first one. Okay, so we're also going to see that intermolecular forces have effects on the enthalpy or heat of vaporization and the enthalpy or the heat of fusion. So this is energy associated with phase changes. So we'll talk about this at the end of this chapter and we'll do some calculations with it. But delta H vaporization is the energy associated with going from a liquid to a gas. And delta H of fusion is the energy associated going from liquid to solid. Okay, so kind of just like our delta H equals Q equals MC delta T, we'll kind of look at this, but this is specific for a phase change. Okay, so the interactions that we see will have an effect on these as well. So kind of think about it. Again, if you're going from the liquid to a gas phase, if you have something like water that has those strong interactions, it's going to take more energy to do that. So we'll see things that have, again, hydrogen bond and that are dipole-dipole, they're going to have much larger heats of fusion and vaporization than something like methane, where you're just seeing those dispersion forces. So those will be much lower. So we won't talk about 3 and 4 too much in this chapter, but surface tension. What surface tension means is if you have, say, the surface of a liquid up at the top, the molecules tend to hold on a lot stronger at the surface. Okay, so that's because we like to form all of these sort of bonds, these hydrogen bonds or these interactions in as many different angles and locations as we can. At the surface, there's no way to form, I'll change to my interaction color. So at the surface, there's no way to form interactions this way. So they kind of double up at the surface. Instead of forming interactions with something above it, it's just going to form doubly strong interactions with its neighbors at the surface of a liquid. So you get more sort of like an increased interaction between molecules at the surface of the liquid. Okay, so next, viscosity, resistance, and flow. We're not going to really talk about this at all, but that you can imagine that does the increased interactions would have a large effect on how a liquid flows. Okay, vapor pressure, we will talk about this one. So vapor pressure is sort of how much of your particles can escape into the gas phase at a given temperature. So equilibrium between the liquid phase and the number of particles that it can escape into the gas phase. And this is dependent on temperature. So we did see this in gas chapter where we had to look up the vapor pressure of water at different temperatures to look at some Dalton's law calculations, like how much water vapor we would have mixed with our hydrogen gas. So same thing, things are going to have a much higher vapor pressure if these interactions are lower. So it's going to be easier to escape into the gas phase if your interactions are much, much lower. Okay, so we'll see that. Again, things that are polar, like water, are going to have much lower vapor pressures. But things that are non-polar are going to have much higher vapor pressures because it's much easier for those molecules to separate from one another to get into the gas phase. Okay, so that's kind of the gist of it. Let's go through a couple of examples. Okay, so at the top of the page here, we're going to look at kind of those things I just mentioned. Okay, so how evaporation and boiling and things like that happen. We're going to see a little diagram here. So I'm going to change color. Okay, so evaporation, so just particles escaping from, a liquid into the gas. So this is kind of like your vapor pressure. So vapor pressure. Okay, so we do know that particles have a distribution of speeds. We learned that from chapter 10 when we looked at that Maxwell distribution of speeds. So in a liquid sample, there are a handful of number of particles that do possess enough energy to escape out into the gas phase. So that's its vapor pressure. Okay, so we just get a fraction of what could go up there at lower temperatures. As the temperature increases, we are actually putting more energy. Those particles are moving faster, so more of them have energy to escape the gas, and we do see that. So for example, if we were to draw, I'm going to kind of draw right here, if we were to draw that Maxwell distribution of speeds, so we had something that looked like that. So let's say to escape into the gas phase, you needed to have this minimum amount of energy. So this is the energy where a gas could escape, or a molecule could escape into a gas phase. So for this blue one, only a small fraction of those right there can escape into the gas phase. So we get this here. What if we increase the temperature? So if we increase the temperature, our Maxwell distribution looks something, say, like this. And that threshold energy is still the same, but now look at this. Now we have so many more because we've increased the energy, and now we have, on average, more particles that have enough energy to escape into the gas phase. So as we increase temperature, we increase the pressure of gas, the vapor pressure. Okay, so boiling represents the temperature where essentially the whole of the Maxwell distribution, we flatten it out so much that most of it is past this threshold. So now the particles have a whole lot of energy, and we start forming gas pockets inside that eventually escape out into the liquid boiling. Okay, so if this was water, we would start to form little pockets of water vapor that eventually, because of their super low density, would escape as bubbles and as gas out of the liquid. So, and again, it's just flattening this Maxwell distribution so that the speeds of this are past that threshold amount for the gas to boil. Okay, so for water, we would expect that threshold to be way down here because of its super strong hydrogen bonds. But what about something like methane? Methane, for example, its vapor pressure might be here. So for methane, for them to escape into the gas, it might be way, way lower because, again, you just have dispersion forces there. It's not, those gas particles are really able to go from the liquid into the gas quite a lot easier. So that's really the only difference here is kind of where that threshold energy falls, and then looking at the Maxwell distribution of speeds, how many of them have that energy to escape. Okay, so a typical vapor pressure plot looks like this here. So this is the one we see for water. And so these are kind of our more room temperatures. I don't know, 50 is getting a little hot. Actually, that's actually really, really hot. So it's kind of flat here. There's not a lot of vapor pressure. So again, we're on the tail end of that Maxwell distribution here. But as it starts to really jump up exponentially, that's where we start moving the top of this peak over and past that threshold energy to go into the gas phase, and then we really see it take off exponentially there. Okay, so and then when it gets to the boiling point there, again, we've essentially flattened this curve out so much that most of the speeds of the particles now have that threshold energy to escape into the gas phase. Okay, so that's fun. So I'm going to do a little bit of erasing here so we can go on to the next part. Okay, so we want to explain the trends that we have in boiling point below. Okay, so we'll start here. We have HF is the highest, then HCl, HBr, and HI. Okay, so seems like HF is really sort of a lot higher than the others. So how can we explain this? So if you're given questions like this, which you will, because this chapter is all about that, first, interaction. So look at the interactions first. Interactions are going to have the largest effect. Second, number of electrons. And 3, if you're desperate, we go to shape. Okay, so let's look at the types of interactions we would have. So HF, so linear molecule, looks like that. Definitely fluorine most electronegative, hydrogen kind of not very electronegative. So this here, we would expect an HF with another HF. So here, kind of draw the interaction. So that interaction we would expect to happen between 2 hydrogen fluoride molecules is hydrogen bonding. Okay, so HCl, HBr, and HI, we just substitute those F's for a Cl, so like a HCl with an HCl, an HBr with an HBr, or an HI with an HI. It's still going to be polar, but they're not nearly as polar. So these all are dipole. Okay, so we've explained why HF is so much higher in terms of boiling point than the other ones. It has a much, much stronger intermolecular interaction. And again, remember to boil, you have to overcome those interactions. Kind of think of it as little magnets. If the magnet is very strong, holding these two together, you need more energy to break it. And that energy is coming from putting in the energy to boil it. Okay, so these ones all have dipole-dipole, so we see kind of a steady increase here. So how can we explain the difference between HCl, HBr, and HI? Well, the answer here is number 2, number of electrons. So HI has the most, followed by Br, followed by Cl. So the difference here, why HI boils at a higher temperature than HCl, is number of electrons. So we have here, we have increasing number of electrons. So because that's happening, these are much more polarizable. HI is more polarizable than HCl. And because of that, it's going to have a stronger interaction. And again, what I mean about that is think of, an iodine atom with tons and tons of electrons. It's a lot easier, for example, to get an uneven distribution of electrons, meaning you can have statistically or some electrons more on one side than the other. So because there's so many electrons, it's easier to create that sort of pole region where possibly you might have a little bit more electrons on one side of this atom than you do the other. But with something like Cl, not as many electrons, so the chances of you getting a good uneven distribution are a lot lower with less electrons. Okay, so now we have CH4, SiH4, GeH4, and SnH4. So C, Si, Ge, and Sn are all in the same family. So they're all forming the same type of molecule here, purple sign. So they're all forming whatever, H, 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 and H, where that X in the middle could be C, Si, Ge, or Sn. Okay, so they all have the tetrahedral geometry, so they're all nonpolar. So they're all only going to experience, at best, dispersion forces. Okay, so no dipole-dipole, no hydrogen bonding, none of that. They're all nonpolar, so they're only going to experience dispersion forces. Okay, so if we look, and that's why they're all so low here. Like these are very, very low boiling points. I mean, look compared to these. So much lower because again, the interaction between them is not at all very strong. Okay, so why do we see a steady increase going from CH4 to SnH4? The answer to this is, here we'll change color. The answer to this is as you go from C to Si to Ge to Sn, number of electrons the same way is steadily increasing. Number of electrons in our central atom is steadily increasing from carbon to silicon to germanium to tin. So the difference in boiling point is 100% this number of electrons. Okay, so as we increase the number of electrons, it becomes, again, more polarizable, like we saw here, which makes the interaction a little bit stronger. Not significantly, because you see kind of the steady increase here. So it slightly makes it, again, a stronger interaction between the two. Okay, so to kind of wrap up this section here, to kind of go back, let's see if I can get a little bit better. Okay, so why can this bug walk on water is the question right here. That's better. So can this bug walk on water? And you can kind of see it right here. Like where his little bug feet are on the water, we see it dimpled in here. Okay, so the answer to this is surface tension. Okay, so if you have a sort of pure liquid of water or anything else, it's very, very polar. You do create this almost skin on the top, where again, you get even greater of those attractions at the surface of the liquid. So the answer here is, again, those larger interactions are going to give you a stronger interaction at the surface in those hydrogen bonds. So again, so if we had a water, it can, so if this one's at the surface of the liquid, there's no way to make hydrogen bonds this way. So when it makes them this way, they're even stronger. So we'll make it super, super. So it makes it even stronger here. Let me fix the glare there, hopefully. Maybe not. Here, I'll have to switch from yellow so you can see. But here at the surface, you can't even see that one either. Aha, there we go. So they're at the surface. Oh no. Okay, sorry. So they're at the surface. They are a lot stronger. There, you can kind of see it now. So our interactions, our hydrogen bonds at the surface are a lot greater because, again, we're missing here where we could form hydrogen bonds, but we're now at the surface of the liquid. It makes it stronger. So you do get increased interactions at the surface of a liquid. Okay, so that is that. Take this away. One last thing I wanted to kind of look at, and that is shape. Okay, so polarizability and shape. Okay, so we talked about kind of the ranking system. First, definitely look at your interactions, and we saw that when we compared HF to HCl to HBr to HI. If you do have one of those stronger intermolecular forces like hydrogen bonding, that's for sure going to win out. Next is the polarizability due to number of electrons. But then if it comes down to it, it's going to come to shape. So for example, we have this molecule here, which has 1, 2, 3, 4 carbons. All the hydrogens, same here, 1, 2, 3, 4 carbons with the same number of hydrogens. Difference is we have what's called an elongated shape, and this one here is more branched. So which shape is more polarizable? Turns out that elongated shapes are more polarizable. So think about a long chain of carbon like this, or like sort of a Claire donut shape, so nice and round like that. Okay, so it's easier to move electrons around in a shape like this. So not only do you get sort of lengthwise, but you have a lot of surface area up here and down here, where something could come in from this direction and push electrons around. Here, the shape is more compact and more spherical, so this is going to make it more difficult to push electrons around. There's sort of very limited spaces to where you can come in. So we would expect the top structure to be more polarizable and have a slightly higher boiling point. So if we look it up, even though they have the same formula, the top structure would have a higher boiling point due to the shape, which it does. So when I looked it up, -1 Celsius for this guy compared to -12 for this one. So again, the difference between these two is just in the shape, where this shape, sort of long chain shape, is more polarizable. So again, think of elongated shape is more polarizable than this one here. And again, kind of if we look, this is shaped more like this. Again, kind of like in a Claire donut, where you can have a lot of surface in here to come in and start moving electrons around. So something polar like water can come in and really start shifting electrons in this. This one is kind of more shaped like this. Not as many approaching angles here to start moving electrons away. So this one, like I said, boiled at a balmy -1 degree Celsius, but this one down here, not as polarizable, so it's going to have a much lower boiling point at -12. Okay, so this one is by far the most subtle. So again, if it comes down to it and you have to consider shape, always choose a shape more like this. But your two larger factors are going to come down to the strength of the interaction and then the number of electrons.